Hello all. So welcome to fourth tutorial, and it's already 4, so let us wait for a couple of minutes if some people want to join. Yes, so we'll wait for like 5 minutes if others want to join, and then we'll start. Yes, good afternoon. Yeah, let's wait a couple more minutes so that. Okay. Yeah, good afternoon. So let's wait a couple more minutes so that if somebody wants to join, they can join. In the meanwhile, if you have any doubts, then feel free to ask.
This the scope of this book, but I was reading about perturbation theory and it is about small
Uh,
perturbation, right?
Ma'am, can you repeat, please? I could not hear you.
Yeah, actually, I was reading about perturbation theory
Yes.
from Zedley
Mm-hmm.
and Griffith.
Yes.
So that is, if the amount of perturbation is very small, only then you can apply that theory. So
Yes.
if I want to learn the variational method and WKB method,
Mm-hmm.
I don't know anything about those two methods.
Okay.
So, can you suggest some books or some, nice materials, course materials, where I can study that?
I think both these methods are also discussed in the books that you mentioned, Griffiths and Zetley, but in
Mhm.
the later chapters, I think. After you complete the perturbation theory, then they come to this. Anyway, so the book that is being followed for this course, which is JJ Sakurai, that
Yeah.
also has a very good and detailed chapter about these approximation methods.
Okay. Okay.
So,
Reading from the book is one thing, but solving the actual problem,
yes,
that
exactly.
is the insight of how actually one has to use that. So,
Right.
like, uh, like you do the problems, so then we are able to make out, okay, this is the way to actually use it.
Yes.
So I wanted something like that.
Ah, okay.
And if there's any issue, can I send you on? Is there any email ID which, if I can approach you?
Yeah,
If I
I
have
can.
any issue on quantum, regarding quantum.
Okay. I can give you my email ID. So,
Are you writing it? How are you sending it?
I'll write it in the chat box.
Okay, that would be great.
So it's just my name and at the rate isc.ac.in.
Thank you. Thank
Yeah,
you so much.
you're welcome. You can what you can do is you can drop me a mail and then
Okay.
I'll try and find out some maybe some question banks or some solved problems or something like that, which will give you a better idea of these approximate methods if
Yeah,
you
thank you. That
want that.
would be of great help. Thank you so
Okay,
much.
no problem. Just drop me an email so that I get your mail and then I'll reply to
Yes,
that.
yes. Yes, thank you.
Yeah,
Thank you.
you're welcome. Okay, so anything else before we start? I think it's already time, so we can start, I guess. Okay. Okay, so before moving on to problems, I'll just say briefly what was discussed in the course material for this week. So there were things like Dirac notation and vector spaces. There will be quite a few overlap with the material from the previous week, right? So for example, this operator algebra and properties like hermiticity, unitary operators, all these things, we already have solved a few problems last week. And this week we will see that there is quite a few overlap. And then there will be things like commutators and eigenvalues and then measurements like what we have already discussed, but some more complex problems. Okay, so with that, let us begin with a very simple problem. And then let's see if we can answer this. So the problem is that we have an operator A which is Hermitian, and then we have another operator B which is iota times A, and the statement is that this is Hermitian. So true or false? Yeah, this is false. Correct. So why is this false? Because of the presence of iota. Okay. So let me just quickly do it. We have B as iota times A. So our B dagger will be iota times A dagger, and we can write this as I star A dagger. Now A is Hermitian, so A dagger will be simply A. So this is just iota times A and then iota star. Now iota star becomes minus iota, so our B dagger is minus iota A. And from this equation, we see that this iota is simply B, so we can write B dagger as minus B. So this is clearly not Hermitian. Do you know what this is called? One second. Yeah. Okay. Yeah, anti-Hermitian. Correct. So when our B dagger is minus B, we call this thing as anti-Hermitian. Okay, so the correct answer is B, false. Pretty simple, right? Let's move on to the next one. Now this is a multiple select problem. It can have more than one option, correct? So we'll do this step by step. The question is which of the following statements about parity operator, so this is about parity operator, are correct. So option A is parity operator P is anti-Hermitian. So is this statement correct or incorrect? Okay. So first of all, what is a parity operator? So as discussed in the lecture, parity operator P. So this inverts the spatial coordinates of the system. Okay, basically R will get converted to minus R. Okay, so if we operate P on a system, so the spatial coordinates are inverted. Okay, so let's look at the first one. The option A says parity operator P is anti-Hermitian. Now, okay. So this statement, okay, do you think this is true or this is false? Now there is a very simple way to think about it. And the way is that we have so basically this P corresponds to a observable property, corresponds to an observable. Okay, yeah, therefore Hermitian. Whenever we have any operator that corresponds to an observable, yeah, the operator has to be Hermitian. So for example, Hamiltonian. The Hamiltonian operator corresponds to energy, and energy is an observable. Therefore, Hamiltonian has to be Hermitian. Same goes for the momentum operator, the x operator, the position operator, the kinetic energy operator, and so on. Okay, so statement 1 is actually incorrect. What about B? So they say P is unitary. So let's check if P is unitary. Okay, so the basically what this means is our P operator, yeah, it is unitary. So our P operator does not change. I'll just write. Yeah. It does not change the normalization of a state, which means that P dagger P is simply I. Therefore, P is unitary. So this statement is correct. Now P square is equal to unitary operator I. Is this statement true or false? Yes, this statement is again true. So why this is true? So when we apply the parity operator twice, it flips the coordinate from r to minus r, and then it flips it again from minus r to r. Okay. So for C, applying P twice, it changes r to minus r and then back to r. Right. So which is essentially like doing nothing. So it is equal to the unitary operator I. Now the last question, no, sorry, the last part is about the eigenvalues of P. So what will be the eigenvalues of P? They are saying plus and minus 1. Is this correct? Yes. Yes, this is correct. And there is a very simple way to find out the eigenvalues. We just saw that let's say we have our unitary operator P and it operates on a wave function psi. let's say it gives some eigenvalue lambda and the wave function psi. So if we operate this again, so as to say we operate p square psi, so then we will get lambda square psi. Okay, so this is operating 2 times. But we know that p square is basically here. P square is nothing but I, right? We know that p square is our identity operator. Therefore, lambda square should be equal to 1. Okay, therefore lambda square should be equal to 1, because this p square here on the left hand side, this is simply identity. So operating on this on psi should give us psi, and that is only possible when lambda square is 1, and this implies lambda is plus minus 1. So these are the two eigenvalues that we get for our unitary this parity operator. So the eigenvalues of p are plus and minus 1. So this is correct. Okay, any doubts in this one? No? Okay. Good. So let's move on to the next one. So here we have two states. Okay. So one state is psi, the other state is chi. Note that both of them are written in terms of phi 1 and phi 2. Right? Phi 1, phi 2, and here also phi 1, phi 2. Okay. What is this phi 1, phi 2? Phi 1 and phi 2 form a complete and orthonormal basis. Okay. This means complete and orthonormal basis. This means that we can define any wave function in terms of phi 1 and phi 2. So they are complete. Also they are orthonormal, meaning they are normalized because they are normal, and they are perpendicular to each other. So they are ortho. Perpendicular meaning their inner product will be 0. Okay. So let's write out psi, and then the problem is the trace of psi chi is minus a over root b, and then we have to find out the values of a and b. Got it? Okay. So let's do this one. So our psi can be written as 9i phi 1 plus 2 phi 2, and our chi can be written as minus iota by root 2 phi 1 plus 1 by root 2 phi 2. Okay, so this is given to us. Now what we have to find? We have to find the trace of psi times chi. Okay, note that both of these, they are in ket form, right? But this chi here, this is in bra form. Okay, so we cannot just directly substitute chi. Now I hope all of us here know what a trace is. Anyway, I'll just write here. Whenever we have a matrix, let's say we have this 3 by 3 matrix. So the trace is given by the sum of the diagonal elements. So the sum of these diagonal elements. So the trace will be A plus E plus I for this case. So this is trace. Okay. Now there are a couple of ways to do this problem. I'll do it by one way, and you can do it by the second way on your own. So one way is that what we notice here is that we have psi like this, and also we can write, okay, let's write the bra form of psi. So what will be the bra form of psi? It will be minus 9 iota phi 1 plus 2 phi 2. Similarly, this will be iota by root 2 phi 1 plus 1 by root 2 phi 2. Okay. Note that whenever you have iota, that gets changed to minus iota. Okay. Okay. So now what we have to do? We have to do psi times chi. So this thing, right? This thing. So we have to take psi here, and we have to take chi here. And then what we have to do? We have to take their outer product, right? So this is outer product. And what we will get is, so this is like multiplying two matrices. Okay. So if we multiply these two matrices, what will we get? We will get a 2 by 2 matrix, right? So the first term will be A times C. Second term will be A times D, and this is BC, and this is B times D. So its trace will be AC plus BD. Okay. So what I am not going to do is, I am not going to perform this. So you can do this on your own, right? So you can then basically write this as A phi 1 plus B phi 2, and then enter these elements like this. You will get a 2 by 2 matrix, find out the trace. You will get the answer. But if you notice, there is very interesting thing happening when we take the trace. So the sum that you see, AC plus BD, this is nothing but the inner product, right? So this is as if we just took dot product if of these two vectors. Okay. This is simply like taking the dot product, which means what we can do is, we can write this trace of psi and chi, we can write this as just the dot product of chi and psi. Okay. Is this step clear? If no, then I can explain. Clear. Okay.
Man, can it be the other way around also? So this trace is the inner product of chi with psi.
Yes.
What about inner product of psi with chi?
Yes, you
Is
will
that
get
also true?
basically the same thing, because let's say because A dot B is B dot A, right? So you can write other way around also.
But in the inner product, when you interchange these chi and psi, then there is a conjugate. That is, we take a conjugate.
Yes, so there you have to take a conjugate. But if you write it in this form, then basically you don't have to take a conjugate. Why? Because here if you note that it was bra chi, right? And then here also it is bra chi, and here it was ket psi. Here also we have maintained ket psi. And if we were to reverse it, if we were to change this ket psi to bra psi and bra chi to ket chi, then what we are doing is we are changing it from bra to ket, right? And then we have to take the conjugate. Is that clear? Like for here the this these things basically they remain the same. So there will not be any conjugate. Yes. If I had taken it other way around, then I had to take the conjugate. So that's why I've written it in a simplest in this simple form where these remain as it is. So I've not changed the bra to kais and kais to bra. Whatever was bra is bra, whatever was ket is ket. So it remains same. Okay, so now yeah. Now it is pretty straightforward, right? Why is it straightforward? Because this phi 1 and phi 2 they are orthonormal. So phi 1 and phi 1 will give us 1 and phi 1 times phi 2 will give us 0. Okay, so this thing, so then okay, so then we have to just so I have highlighted these two in the blue. We have to focus on these two, and the coefficients of phi 1 is here it is 9 iota and here it is iota by root 2. So this will be 9 okay, let me write the chi first. So it will be iota by root 2 multiplied by 9 iota, and then plus here we have 1 over root 2 and it is just 2 multiplied by 2. That's it. Okay, so this is 9 iota square, which is minus 1. So this is minus 9 over root 2 plus 2 over root 2. Okay, which becomes minus 7 over root 2. Okay, and okay, minus 7 over root 2. Sorry. So if we look at the question again, they say that it has to be in the form of minus a over root b, minus a over under root b. So if we just compare, a is 7 and b is 2. So a is 7 and b is 2. Okay. So just to cross check, you can also form this matrix by taking the outer product and then see that the trace comes out to be the same or not. It should come out to be the same, but just to cross check, you know. Okay. Little homework. So one second. हाँ 6 बजे तक क्या करना है तो ले ले कुछ दिक्कत है बोलना मत ज़्यादा बस मतलब ज़्यादा शोर मत करना बस कोई दिक्कत नहीं है शोर होगा क्या ठीक है कर ले क्या ही करना तू बंद कर दिया था वो sorry. So okay, let's continue. So here we are given a commutator A B C, commutator of BC, and then we have sorry D. Okay, and we have to find out this. So note that we have an operator A here which is commuting with this entire thing. Okay, so this entire thing, which is the commutator of B and C multiplied with D. Okay, so to solve this, let us write this commutator of B and C. Let us write this thing as K. Okay, so then our K is nothing but BC minus CB. Good. And then this thing becomes A time, oh sorry, commutator of A with K times T. And this we can expand as A times, okay, sorry, this will not be K. A times KD minus, yeah, and now we can substitute back the value of K. So this will be A and then BC minus CB times D minus BC minus CB times DA. And then if we open these brackets, we will get ABCD minus ACBD minus BCDA plus CBDA. Okay, so this is what we'll get. Let's see if it matches with some option. Okay, it matches with option A. So here we have ABCD, ABCD, then minus ACBD, minus ACBD, minus BCDA, minus BCDA, and plus CBDA, and plus CBDA. Okay, so option A is the correct answer. Okay, so moving on. Now we are given V. Okay. So we are given V as 4 plus 3 iota times V1 and minus 4 e to the minus 3 iota pi by 2 V2. Okay, and what we have to do? We have to find the norm of V. And they say that the norm of V is root A, and we have to find out the value of A. So for any wave function, let's say for any general wave function psi, if it is written as c1, c2, c3, so on. So the norm of psi will be then mod c1 square plus mod c2 square plus mod c3 square and so on. Okay, this is how norm of any wave function is defined. Okay. Also we must notice that this v1 and v2, they are orthonormal pair. Okay. So and this c1, c2, c3, what are these c1, c2, c3? They are the coefficients of these orthonormal pair of kets, right? So just by comparing, here we have c1 is 4 plus 3 iota and c2 is minus 4 e to the minus 3 I pi by 2. Okay. Now what we have to do, we have to find the mod square c1 and mod square of c2. So what are these? These are just two complex numbers. 41, I think. I think you are correct. Okay. So what will be mod c1 squared? It will be nothing but 4 squared plus 3 squared, right? So this is a complex number. The mod is defined as just the under root of square of real part plus the imaginary part, but because here we have another square, so this is 25 plus 9. Oh sorry, this is 16 plus 9, which is 25. Similarly, mod c2 squared. Okay, this is already written in the form of this magnitude and phase. So here it becomes very straightforward. This will be minus 4 squared, which is 16. Therefore, norm of V will be mod C1 squared plus mod C2 squared, which is nothing but 25 plus 16. And there will be a square root here. That I forgot. Okay. And also there will be a square root here. Okay. Oops. So this is under root 41. And the norm of V is of the form under root A. If we compare this with under root A, we get A as 41. Okay, all good? Okay, then let's go to the next problem. So we have a three-dimensional vector space and we have three orthonormal bases, 1, 2 and 3. We are given alpha and beta in terms of these two. So alpha is iota times 1, minus 2, 2 and minus iota 3. Beta is iota 1 and then 2 times 3. Okay, and what we have to do, we have to find the inner product in terms of a and b. So we are already given that the inner product will be of the form a plus bi, and we have to find what is a and what is b. Okay, so let's do one thing, because here we have this ket form. Let's change it to the bra form. So we will have a minus 1, b minus 2. uh, okay, let's check. i I think there should not be a minus sign. Let's check. So this beta will be minus I 1, and then this 2 remains 2, and then 3. Oops. Okay, so now to take the inner product, so our alpha and beta, so we have to now focus on this one and this one, these two. So this will be, so from here we'll get iota, and from here we'll get minus iota, and then this minus 2 will be multiplied with 0, because we don't have any 2 get here, and then this minus iota will be multiplied with 2, I guess. Yes. Okay. Hmm. So this is minus iota squared, right? And this is 0, and this is minus 2 iota. So iota squared is minus 1, so this is 1 minus 2 iota.
Manu, इसमें of alpha rather than beta.
Oh yeah,
Taken.
yes, I'm sorry. Yeah, okay, so let's do this again. Uh, or we could have just taken the complex conjugate of this 1 minus 2 iota, which would have given us 1 plus 2 iota. Let's see if we get the same thing. Okay, so yeah, I'm extremely sorry. So this will be minus iota, minus 2, and then plus iota. Okay, and then we'll multiply these two together. Okay, so alpha times beta. So now this time we'll have minus iota times iota, and then minus 2 times 0, and then iota times 2. Yeah, so this will give us minus iota squared. This is 0, and this is simply 2 iota. So this is 1 plus 2 iota. So comparing with this form, we have A as 1 and B as 2. So A is 1 and B is 2. Okay. Why did you get the negative signs? I didn't understand.
No, sorry, I didn't take the complex conjugate. I just
Ah,
simply
okay.
multiplied.
Okay, okay. Got it. And I took the conjugate of the wrong one.
Yeah.
Okay, no problem. So, yeah. So this seems correct now. Okay. So let's move on. Okay. So we are given one unnormalized state, which is given in terms of three orthonormal vectors. So this phi 1, phi 2, phi 3, they are orthonormal. Phi 1, phi 2, and phi 3. So they are orthonormal, but not psi. It is explicitly mentioned that psi is unnormalized. Okay. Also, this phi n, any phi, they are eigenstates of operator B, such that when we operate B on phi n, we get n squared times phi n, and n is 1, 2, or 3. Okay, n is 1, 2, or 3. So our eigenvalues are 1, 4, or 9. And what we have to now find is expectation value of B. So expectation value of B, right, for the state psi. For the state psi, and it will come out to be of the form A upon B, and again we have to write down what is the value of A and what is the value of B. So what is our psi? Let's write our psi. 1 by root 2 phi 1 plus 1 by root 5 phi 2 plus 1 by root 10 phi 3. Okay. So this is our psi, and we know that the eigenvalues are 1, 4, and 9. Now how do you define the expectation value of B? So we write B as, now if this psi was normalized, this would be sufficient, but because psi is not normalized, we'll have another term coming here. Okay, so this will be our uh, expectation value of B. Okay, this is just how it is defined, right? So you operate B on psi and then integrate over all space, and then you basically divide by this normalization. So let's first calculate what this normalization will look like. Okay, so what will be our psi times psi? Now if you look here, all these numbers, they are real numbers, right? There is no iota present, so we can simply just take their squares and add them. So this will be like mod of this squared plus mod of this squared plus mod of this squared, and because they are all real, so mod is basically the same value. So this is 1 by 2, 1 by 5, and 1 over 10. And if we take the LCM to be 10, so this will be 5, and this will be 2, 7, and this will be 8. So this will be 8 over 10 or 4 over 5. Okay, so we have evaluated the denominator, and we know that this denominator comes out to be 4 by 5. So we can write our expectation value of B as 5 over 4, psi b psi. Okay, now we will evaluate the second part. Okay, okay, so when b is okay, so what is b? Whenever b operates on any phi n, it returns the same phi n, and the eigenvalue is n squared. So when it will operate on phi 1, it will give you 1 squared. When it will operate on phi 2, it will give us 2 squared, and when it will operate on phi 3, it will give us 3 squared. So let's operate b on psi. Okay, this is our wave function. So our b on psi, so this will be 1 over root 2, and b operating on phi 1 just give us 1 squared. Okay, I'll just write 1 squared, and then same phi 1. Okay, and then here you will have 1 over root 5, here it will be 2 squared, and here it will be 3 squared. Sorry, this will be root 10. Yeah, and then phi 3. Now this is what we get. Now let's take the inner product of this thing. So while taking the inner product, again these are all real numbers, so we don't have to take the complex conjugate. So just multiply this thing with 1 by root 2. So this will become 1 over 2. Okay, let me write explicitly. Okay, and here we'll have 1 by root 5 into 1 by root 5 into 4, and here we will have 1 by under root 10, 1 by under root 10 multiplied by 9. Okay, so this is 1 by 2, and this is 4 over 5, and this is 9 over 10. So if we take LCM, this will be 5 plus 8, 13 plus 9, 22. So 22 over 10, which means 11 over 5. 11 over 5. Okay, so then if we go back here, so basically this term is 11 over 5. So this 5 and 5 will cancel out, and what we will have the final value as 11 over 4. Okay, so our expectation value of b is 11 over 4. Now it has to be of the form a over b, so a will be, sorry, a will be 11 and b will be 4. Okay, any doubts in this? Yes, no, clear? Okay, good. So now we know how to find out the expectation value. So just keep in mind that we have to just make sure that if our wave function is not normalized, then we first normalize it. Okay, so this is our normalization condition. Okay, otherwise we will make some mistake. Okay, good. So then here we have similar problem. Again we have a pair of orthogonal kets, so they are orthogonal kets, and then what we have is we have been given that we have a ket V, which is defined as 5 minus 3 iota, v1 plus 3 exponential minus I 3 pi over 2 v2. Okay. Now, what do you mean by dual of the kit? What does this mean? Anyone? Basically, what we have to do in this problem? What does finding a dual of any kit mean? Yeah, bra of v. Yeah, exactly. So basically, the problem is what is v, right? And this we have already done so many times in our sessions. So this should be pretty straightforward. So we know what we have to do. We have to take the complex conjugate of these coefficients, and that's it. So this 5 minus 3 iota, this will become 5 plus 3 iota v1, and this 3 remains 3, and this exponential part becomes minus iota becomes plus iota, and 3 pi over 2, and v2, and that's it. This is our answer. So which one is it matching with? Yeah, option B, I guess. Yes. So option A and B are same. Notice that here in option A they have written it in ket form, which is not the dual, right? So option B is correct. Okay. Yeah, this was pretty straightforward. Okay, so yeah, okay, so before solving this, let's take a 2 minutes water break and then we'll resume. Okay. Okay. So I think this is problem number 9. Let's start. So we have been given an operator B as ket phi 1 bra phi 2, where phi 1 and phi 2 are orthonormal. Again, these two are orthonormal. And then we are asked about B squared and B times B dagger. Okay. So first of all, let's calculate what will be B squared. Okay. So B squared will be given by phi 1, phi 2, and again phi 1, phi 2. Okay. Now we can write this as phi 1, phi 2, phi 1, phi 2. Okay, so now what happens to this middle term? This term, because they are orthonormal, so the inner product of phi 2 and phi 1 will be 0. So then what we can conclude is that our b squared, this is 0. Okay, now the other one is b times b dagger. B times b dagger. So firstly, what will be, okay, let me write on here. What will be our b dagger? If our b is given as phi 1, phi 2, so b dagger will be phi 1, phi 2 dagger, and this we can write as, so this phi 2 will come first, right? This is the product rule that we discussed in the last class also. So basically the AB dagger becomes B dagger A dagger. So this phi 2 dagger, so this will become phi 2 phi 1. Okay, so notice here that this B is phi 1 first, then phi 2, and B dagger is phi 2 first, then phi 1. Okay, so this B times B dagger, this will become phi 1, phi 2, phi 2, phi 1. Okay, and because they are orthonormal, so this will be just 1, right? So our B times B dagger will be simply phi 1 and phi 1. Now what is this? Okay, what is this? This thing? So this is called projection operator, right? Projection operator on state phi 1. And its property is that it is Hermitian. It is Hermitian and it squares to itself. Meaning that if we take B dagger square, we will get B dagger. Okay, now let's look at the options. So clearly, first option is wrong because B square is not 1. Again, second option is wrong because B square is not 1. Option C is correct, right? B square is 0 and B dagger is a projection operator. And option D again is incorrect because B square is 0. Yeah. Is this clear? Yes, okay. So I hope you all know what projection operator does. So it just takes the projection of any wave function along, let's say in this case, phi 1, right? Yeah, so that is what projection operator does. Okay, so let's go to the 10th problem of the day. It's a true and false problem. The parity of both the position operator R and the momentum operator P are odd. Okay, true or false? Well, let me ask you, is it true or is it false? Okay, first of all, what does an odd parity mean? Okay, so in the previous one of the previous problem, we discussed that uh, the transformation basically happen. Let's say we have any operator O, we have any operator O. If it goes to minus O, then this is odd parity, and if it remains as it is, if it remains just as it is, then it is even parity. Okay, and this is both of them, they are after parity transformation, after parity transformation. Vandana Arora, true, yes, so this is true. Now the position of, to understand the position operator, it is very simple, because we know what happens under parity. Under parity our r goes to minus r, right? So this happens to our position coordinates, so definitely our position operator will also change its sign under parity transformation, it will go to minus r. So this is odd. Now let's talk about the momentum p. Okay, how do you define p? It is defined as minus iota h cut, and then this del, or just del by del x in one dimensions, right? Now under parity, this gradient also changes sign, so this del goes to minus del, because it is a derivative with respect to x. Okay, so this is like same things, because r is going to minus r, so it's the derivative with respect to r will also change the sign. Therefore p will also go to minus p, right? So r is going to minus r and p is going to minus p, so the parity of this thing also is odd. Okay, and the statement is that the parity of both the position operator and momentum operator p are odd, so this thing is true. Got it? Now can you give me one example of an operator which has even parity? Energy operator, correct. Okay, because energy operator will have a double derivative, so the parity will change twice, right? Because there we will have p squared, right? So parity is changed twice, so it becomes even. Similarly, you can define an operator, let's say r squared or x squared, so that will also be uh, even parity. Okay, so I hope this is clear. Let's move on to the next one. Okay, so here we are given two Hermitian operators. A and B, and we have to show that AB plus BA is Hermitian and AB minus BA is not Hermitian. Okay. So how do you do this? So we are given that A and B are Hermitian. So what we will do to show that AB plus BA is Hermitian, we will take its conjugate, right? AB plus BA dagger. Now this will be AB dagger plus BA dagger, and this we know becomes B dagger A dagger plus A dagger B dagger. So this becomes BA plus AB, or we can again rewrite it as AB plus BA. Okay, so this implies Hermitian. Yeah, pretty straightforward. Now what about AB minus BA? Okay, now when we will have AB minus BA, and then we take this dagger, so this will be AB dagger minus BA dagger. So this will be B dagger A dagger minus A dagger B dagger, and this will be BA minus AB, or if you have to write, we can write this as AB minus BA. Okay, which implies, okay, so this is, okay, which implies this is anti-Hermitian. Yeah. Fine. Okay. Hmm. Okay, so then let's do this. So we are given a commutator, and we have x comma h, where h is our Hamiltonian operator, and we have to show that this is minus h cut square by m. Okay, so first of all, the first thing that we need to do is we need to write h as p squared over 2m plus v of x, right? And then first let's calculate what we will get with x comma h. So x comma h will give us x comma p squared over 2m plus vx. Okay, so we can write this as 1 over 2m x comma p squared plus x comma v of x, right? So note that the second term, it has x in both places, right? So it has x in both places, so this one just goes to 0. And for this x comma p square, we can write this as 1 over 2m. We can write this as x comma p, sorry, the commutator of x and p multiplied with p plus p multiplied with x and p. Okay, and this is x comma p commutator is iota h cut, so this entire thing becomes 2 iota h cut, so this is 1 over 2m multiplied by 2 iota h cut. So this 2 cancels out, and we are left with iota h cut over m, and then this p operator. Okay, and then if we take another commutator with x, so basically this thing, so this becomes x comma iota h cut over m and p. So this iota h cut over m comes outside, and this is x comma p. And again, this is just, this term is iota h cut. So this is minus, okay, so this is just iota squared h cut squared over m, and this iota squared is minus 1. Okay, so basically the same thing, minus h cut square m, and we also get minus h cut. Okay, so for this one, basically what we are given a wave function psi, okay, which is written in terms of sine functions. So sine of k1x, sine of k2y, sine of k3z, and we have to show that this is an eigenfunction of the Laplacian operator, and then we have to determine the eigenvalue. Okay. So first of all, what is Laplacian operator? So this is Laplacian, and it is defined like this. Basically the second order partial derivatives. Okay. Similar to particle in a 3D box. Exactly. That's why if you see the wave function, it also has the form similar to particle in a box. Meaning to say that it is also like sinusoidal. Okay. Now, how do you show that something is an eigenfunction of some operator? So for it to be an eigenfunction, del square psi should be equal to lambda times psi. Okay, but lambda will be our eigenvalues. Now let's take derivative of the partial derivative of psi with respect to x. So what we will get, basically the del over del x of this entire thing. So this sine k1x, sine k2y, and sine k3z. Now because this is a partial derivative, so these two terms, they are treated like just some constants. So they'll remain as it is, and we have to take derivative of sine with respect to x. So this becomes cos, and we have one k1 coming out, right? So this becomes k1 cos k1x, and the other two terms, they remain the same. Okay, now let's take the second order derivative. So it will be del by del x of this entire thing, k1 cos k1x, sine k2y, sine k3z. Okay, and again these two terms will remain as it is, and we'll differentiate cos with respect to x, which will give us sine and minus sine. So this will become minus k1 squared sine k1x and sine k2y and sine k3z. Okay, now note that this thing in the brackets, this is nothing but psi. So what we get is our del 2 psi over del x square is nothing but minus k1 square psi. Yeah. Similarly, similarly, we can show that del 2 psi over del y squared will give us minus k2 squared psi, and del 2 psi over del z square will give us minus k3 squared psi. Okay, and this is our Laplace operator, right? You see, we have to add these three. So if we operate the Laplace operator on psi, it is nothing but this del 2 psi over del x square, okay, these three terms, plus del 2 psi over del y squared plus del 2 psi over del z squared, and adding these three, so we get minus k1 squared minus k2 squared minus k3 squared times psi. Let's take the minus sign common and write this as this thing. So this is our equation that we have now. Okay. Now if we compare this to what we have written earlier in terms of lambda here, that our del square psi is lambda psi, it is of the same form. You can see del square psi is lambda psi, and here lambda is minus k1 square plus k2 squared plus k3 squared. Okay, so this is our eigenvalues. Therefore, we have shown that this Laplacian operator is an so this psi is an eigenfunction of this Laplacian operator, and the eigenvalues will be, so these eigenvalues, they are nothing but this minus k1 squared plus k2 squared plus k3 squared. Okay, and we have also shown that this is an eigenfunction. Yeah. Any doubts in this?
Any application of this?
Uh, I don't think so. But you can see that, okay, this lap, okay. So when we consider like particle in a box, like those are 1D problems. So this is a 3D version. Okay. So basically what this means is, what this problem is trying to say is, you can think of that you can consider a special case. Okay, so what comes to mind when you see these things, if I may ask? So this is like p square terms, right? So our p is proportional to just del by del x, so our p square will be this thing, right? And then we divide by 2m, so we get energy. So Laplacian operator basically is our energy operator in three dimensions. And for this case, because we do not consider any potential, let's say V is 0. So this will be like a particle in a three-dimensional box problem, as someone mentioned in the chat also. Yeah.
Yeah. So will it give me, you said that this, the Laplacian will
Sorry,
convert
sorry, I didn't hear you. Can you repeat?
the Laplacian will be similar to the energy of a
Yes.
particle in a three-dimensional world.
Kinetic energy. Yeah, kinetic energy.
Kinetic energy in a three-dimensional world.
Yeah. So this Laplacian operator is basically you divide by this 2m and then you get this. Yeah, Schrodinger of the solution of Schrodinger equation.
Okay.
And now the thing to note is that this wave function psi, it is a sinusoidal wave function, right? So if you consider that you only have your kinetic energy term, which means that your potential energy is 0, and let's say you consider a confined system like particle in a 3D box. So what you are getting here is you are getting a wave function which is in terms of which can be written in terms of sine functions, right? A product of three sine functions, one along x, one along y, and one along z, right? Which basically means that at some boundary, so this k1, k2, k3, they will be determined by your boundary conditions, respectively of x, y, and z. So what is your confinement length? Let's say x1, y1, z1. So then this wave function should go to 0 at those lengths. So then you can write this k1, k2, k3 in terms of the confinement length. And essentially what you will get is that your wave function is an kind of an oscillatory wave function when your system is confined.
So this will be odd solution, right? Odd
Sorry?
solution. This is the odd solution.
Yeah.
Even will have all three cos, or will there be any solution which will have a combination of cos and sine?
So if you take a cos function, I mean, it depends on your boundary conditions. Okay, so let
Okay.
me. It can become cos. Okay, let's
Cos
say.
is the function.
Okay, let's consider this as our x-axis. Okay, if your boundary condition says that this function has to be 0 at 0 and then a. So this is our confinement conditions. So then of course it cannot be a cos function, right? If you put x as 0, right? If you put x as 0, we should get 0, right? Because wave function here must vanish. So for this case it will be a sine function, right? But let's say I can take, instead of 0, I can take my vanishing to be at some minus a, where 0 it necessarily may not be 0, right? So and then if this if I have chosen this a such that this k1 times a, if k1 times a is, let's say, 90 degrees, right, or pi by 2, right, or I can choose this a as pi over 2k, like this, then it will be a cos function, right? Then it will get converted to a cos function, because then when I when I put this k1 as pi over 2a, if here it will be pi over 2a, so then when this x becomes a, let's say when this x becomes a, so this will be pi by 2, so this has to be a cos function, so that our wave function vanishes.
Okay.
Make sense? And then maybe you have different boundary conditions for y, so it can remain sine if the boundaries are such that, let's say, it is from 0 to some b, right? So then it will remain sine. And again this z, it can have some arbitrary values, not necessarily just cos or sine, but a combination of both. such that at that particular value, when you take the sum of those two, sine and cos, you should get 0. Okay?
Thank you.
Yeah. Okay. Okay. So let's do this one. So we have to check whether the operator minus iota h cut x d by dx is Hermitian. Okay, what do you think? Will it be Hermitian or not?
I think it will not be because minus I h bar del by del x is momentum,
Yeah.
which is Hermitian,
Yes.
and x is the position operator, so that is also Hermitian.
Yes.
Hermitian, the product should be the Hermitian.
Sorry.
Is it the product of two Hermitian will be
Will it be Hermitian?
the product of two should be Hermitian. So that makes it Hermitian.
Okay.
If you
Not
ask me the
not
case,
necessarily. Okay. Let's see.
okay, okay.
It depends if the it depends on their commutator. So let's solve this one. Okay. So let's consider that this is some vector a. Okay. So our a is minus h cut x d by dx. Okay. For it to be Hermitian, this should be equal to a dagger if Hermitian, right? This is the Hermiticity condition. Hmm. Now notice that this minus iota h cut d by dx. Okay, so let's write this as like this. Let's write it as x here, and then minus iota h cut d by dx here. Okay, so this is nothing but our, so this is our position operator. Okay, this is our position operator, and this is our momentum operator, which implies we can write our a as x times p. Now if we take the adjoint, so the adjoint a dagger will be simply this thing, right? And then we can write it as, sorry, p will come first, yeah, and then x will come second. Now we know that p and x, they correspond to momentum and position, so the real observable quantities, so they must be Hermitian. So we know that p dagger is p and x dagger is x. So our a dagger, it becomes px. Note that here our a was xp, and now our a dagger is px, right? Now from this commutation of x comma p, we can write this as xp minus px, right? And this we know is equals to iota h cut. We know that these two, they don't commute with each other. Okay, so since they don't commute, we can write our p times x as xp minus iota h cut. Okay, and this px is nothing but our a dagger. This is a dagger, right? And this xp is nothing but a, and we have an additional iota h cut here. Okay, so to write it out finally, a dagger is a minus iota h cut. So not Hermitian. Okay. So although both X and P are Hermitian, their product necessarily need not be Hermitian. Why? Because they don't commute with each other. If you have two Hermitian operators and they also happen to commute with each other, then what would have happened? Then this Px, in case they commuted, could have been written as xp, and then a dagger would have been equal to a. But that we can do only when they commute with each other. Okay. When we have operators which do not commute with each other, then basically we don't get a Hermitian operator. Okay. Yeah. Any doubts in this?
Can you give an example of two observable operators which are anti-commutators of each
Which are anti-commutators?
other? I mean, can observable operators be anti-commutators also?
Uh, okay, so you mean their product, right? So let's say you
Yeah,
have one operator A and one B, and both are observables. So then A multiplied B should give you minus, if you take basically this thing, right?
yeah,
So A B dagger gives us minus B, sorry, minus AB, right?
yeah.
And because both of them are some observables, right? So then
Mhm.
A dagger and B dagger has to be the same. Okay, so let me check. So what that means, so if you take this dagger, so you will have B dagger, A dagger, and this will be nothing but BA. And if this has to be equals to minus AB, for this condition to be true, we must have BA plus AB to be 0. Okay, so the condition is that your A comma B is 0. But again, like, I don't know of such operators. Okay, maybe I'll try to find
Okay.
out and
Yeah,
we'll see. You can also find out. I
yeah.
think just simple googling like example of
Okay.
two operators which anti-commute with each other
Yeah.
will give us a anti-Hermitian this thing. Okay. Okay. Any other doubt? Anyone?
Are there more questions?
Uh, I don't have any, but we have some time. We have like 20 minutes remaining, so I
Okay.
can find out a few more.
Okay. In the meantime,
Yeah.
like we did a problem on trace of a matrix.
Yes.
So trace is the addition of the diagonal
Diagonals.
elements,
Yes.
right? That means the trace of a matrix is equal to the sum of the eigenvalues also.
Yes. Correct.
Now, if we have if there are two matrices which have same trace, can they have different eigenvalues?
Uh, okay. So this trace is not necessarily eigenvalues, but what we have, like, let's say for example, what I mean is, like, for example, if you like here we don't actually have any operator, right? We just have a wave function. Eigenvalues will come when we have some operator acting on it. Okay, and then once that uh, I think you are confusing between two different things. Okay, so let's do one thing. Let's consider this case, and then you can tell me what you want to ask me.
Okay. There are certain matrices which can be diagonalized.
Yes.
So if a matrix can be diagonalized, that means the diagonal element now become, I mean, should they become the eigenvalues in that case? If I want to diagonalize a matrix,
Hmm.
will the diagonal elements be eigenvalues?
Right. Okay, so let's take simple 2 cross 2 matrix. Right. Let's say we have these A B C D.
Mm-hmm.
Okay, and then let's say we have some operator O, which basically returns this same matrix again, and some value lambda. Then this lambda is, we call this as some eigenvalue of this operator O. Right. Now, what should be the form of this operator? Can you tell me?
No, no, I don't know.
Hmm? So basically, okay, it can, okay, let's say it has any form. So to find out this lambda, what we need to do, we need to multiply, how will we write lambda? We have to take inverse on both the sides, right? Like this. Yeah. But if we do this, then this side just becomes
Identity.
identity. So this is kind of, this will give you some null result, right? We don't want that. So instead what we do, we, because this is just a number, this is just a number, this is not any operator. So we take the inverse on the left side. We do this, right? We can do this. And then here also on the left side. Now we will not get identity. Correct. But here we'll just get lambda. So basically we can write lambda as this inverse ABCD, and then O, and then ABCD. Right? So this is a very complex form. And as you said, if we can diagonalize this matrix, right? If we can diagonalize this matrix, then this becomes very simple, right? Let's say it can be diagonalized. So then the let's say this ABCD, let's say we can write it like this: lambda 1 0 0 lambda 2. Then in this case, basically what we get on the diagonals is the eigenvalues. Okay, so the eigenvalues are these diagonal elements. Okay, but in the problem that we were solving, we were not finding eigenvalues here. Okay, we are not finding eigenvalues, but we are finding this, the trace, right, which is this sum of these diagonal elements. Okay, and notice that we don't have any operator here. So mm, we don't operate anything on our this matrix, right? So we will not get any lambda as such. Okay, so we just have, you can think it in terms of like you have two vectors, something I cap plus something j cap, and again here also something I cap plus something j cap, right? So if you basically, okay, let's continue with this our example here. Hmm. Let's say this is one vector and this is our second vector. So if we just take the dot product of these two, So we'll get AC plus BD, right? But then if we take the uh, if we if we take the outer product, as to say, so then we have to multiply. So then we have to consider this matrix AB CD, and then if we multiply, then here we'll get AC. Here we'll get AC AD and BC BD, and now here the trace that you will get is again AC plus BD, right? Which is same, right? So this thing has nothing to do with eigenvalues, right? So it's just that the trace of the outer product, so trace of the outer product is just inner product, if that makes some sense.
Yes, this problem is clear, but I am just asking away from this problem that if two matrices have same trace,
If
is
two
it
matrices have same trace,
same trace, is it possible that they don't have same eigenvalues?
yes, I think it is completely possible. So for example, you can have these two. One is this, one is this. Because they are diagonalized, we know that the eigenvalues of the first one will be 2 and the eigenvalues of the second one will be 1 and 3. And note that this is degenerate and these are non-degenerate, right?
Hmm. Right.
So trace is same in both the cases, but the eigenvalues are completely different.
Okay, in this case, then how are these two? Because trace is a very important parameter when we do quantum.
Yes.
So how these two matrices are then related? That they have the same trace, but they don't have the same eigenvalue. So what other properties they share? What other common properties they share?
So one
Because their
property,
traces are equal.
yes, yes.
But
One property that you can clearly think of is that the expectation value that you will get will be the same, right? Because the expectation value will is like taking inner product, right? And because we know that the inner product is just trace of this thing, right? So trace is same in both the cases,
mhm,
right? So the inner product is same in both the cases.
mhm,
So the expectation values will be same. So for example, if you have, so this is as into saying, let's say you have two particles, okay? Let's say this is energy state, okay? This is energy state 1 and 3 and this is energy state 2. Let's say you have two particles, one is here, one is here.
mhm,
I don't know why I have spins, doesn't matter. Okay, so let's say I have this one particle here, one particle here, and then here I have both particles here. So if you find out the expectation value for both the cases, it will come out to be 2, right?
okay, okay.
For both of them. So if your trace is same, then your expectation values they'll remain the same, right? So this I can one thing that I can think of is that let's say you have degenerate states, and then as you said, like you have some perturbation in your system, so
Mhm.
that will lift that degeneracy, right? So
Yes.
this delta E comes here, right? So this delta E comes here, and now if after this delta E, if this trace remains same, then their expectation value will remain the same.
So you mean to say that before the perturbation, the condition was 2,
Yes,
the definite state, and after the
yes.
perturbation, it became 1 and 3.
Yeah, yeah, because
The
what
expectation value,
perturbation does is it lifts your degeneracy, right?
how it lifts the difference.
It lifts the degeneracy, so you'll get something like this. But the expectation value, if you calculate, you'll get the same thing. Now, that is only when these are like spin 1 fermions, so that one is occupying this state, one is occupying this state. If both of them occupies this state, then the condition is different, right? Then we cannot say the same thing. We can only say this if this particle occupies this state only once. Yeah.
And does it have anything to do with, I just read here, singlet and triplet states. I don't know much about them, but any correlation with this?
Uh, no. So basically, singlets and triplets, they are like spin states when they are like parallel or anti-parallel, right?
Yeah.
I I I'm not sure as of now,
Okay.
but okay, I'll make a note and we'll discuss in the next class.
Thank you.
Yeah.
Any other thing, like apart from inner product being the same, any other quality? Maybe we can discuss it in the next class, but I'm just curious.
Yeah.
Okay.
Hmm. Okay, I'll look for this thing.
Yeah.
If so, basically the your question is, if I have to reframe that, if our inner sorry, if the trace is same but eigenvalues are different,
Yes.
what all information can we like say about
Matrices.
our system?
Same,
Yeah.
huh? Yes, yes, yes.
Okay.
How are the two matrices with same trace but different eigenvalues?
Yes, I got
They
it.
can be related, what properties they share,
Yes.
what
I
information can be obtained. Yes.
Yes. Okay. No, that's actually a very nice question to think about, and I'll definitely think about it.
Thank
Yeah. Okay. Any other problem? I think session is almost done.
you. Maybe we can do one or more problems if you have.
Okay, let me quickly find out one problem and then we'll see.
And if you can discuss in the next class, like this case you discuss on degenerate and lifting of the degeneracy,
Yes.
and then the expectation value remains the same.
Yeah.
Can you discuss it maybe in the next class? What actually physically it means?
Sure.
There are two electrons
Sure.
degenerate and then they are lifted, and what do you mean by the expectation value
Okay.
remaining the same?
Got it. Okay.
Because I feel
Let's.
that if there is
Yeah.
a perturbation
Mm-hmm.
which lifts the
Yeah.
degeneracy, then that means now the conditions have changed.
Yes.
So if the conditions have changed,
Hmm.
then how will their expectation value not get disturbed by this perturbation?
So expectation value is like taking the average of the ensembles, right? So okay, so yeah, so you're correct. So okay, we can wrap up with this. Then we don't need to solve any problem. Let's say we have these two electrons, right?
Mhm.
And then they are in this state, and then we have some perturbation. Let's say some crystal field or something, some perturbation in the system, which lifts the degeneracy, right? So generally, what we have like both these electrons can occupy this state, correct? Because one is spin up, one is spin down,
Mhm.
and uh, yeah, and that's the case. So then in this case, we will see a difference, right? We'll see a difference. Why? Because now our energy is lowered.
Yes.
Okay. But if it happens such that one electron goes here and one goes here,
Now the spin has also reversed.
it doesn't
But
matter. You
one
can
has
have any spin. You can have any spin.
But that
because
possibility is also there, no? That both these things now become up. Is this is also one of the possibility? If you have four
uh,
possibilities, maybe
yeah, there will be multiple
four cases,
possibilities, right?
multiple, up, up, then up, down, and then both maybe registered up, down.
Yes, so that's like the singlet and triplet thing, right?
Yeah.
Yeah, okay. So, but if it happens in such a way, then you will not actually be able to measure any difference in the energy, right? So here your energy will decrease, but here it will remain the same.
What about the energy utilized in flipping the spin of one of the electrons?
Uh, there will not be any energy. Okay, maybe there will be.
Or maybe it is just the relaxation that when it goes up, then both are in the same direction. Then it corresponds to more stable state, maybe. So I don't know. I'm just
Yeah, yeah. I think okay. I think this spin is little confusing. Let's just consider some bosons, where you have just two particles. Okay, even spin particles. Yeah. Now it's fine, right?
and the third case is both are up.
Yeah, we can have third case both are up. But the thing is, okay, this will be the ground state, right? This will be the ground state because
Okay.
here we have the minimum energy, and this will be our first excited state, and this will be our second excited state. So the left side is same in all cases, right? So I'm talking
Mhm.
about the right side. So for the ground state, it is you'll see that there is a difference in energy. But for the first excited case, if you calculate the expectation value, basically you will get the same thing here on the left side and same thing here on the right side, because one particle's energy has increased while the others has decreased. So the
Mhm.
average of these two will be the same,
Okay.
right? So the expectation value will remain the same.
Okay.
But if it then goes to the ground state, then the expectation value will be lowered, and for the second excited state it will be higher. So this was the case that I mentioned here, right? So here from this degenerate states 2 and 2, like the degeneracy is lifted to 1 and 3, the trace is same. Oh, sorry, the trace is same, but the eigenvalues are different. So one property that I could think of that remains same is the expectation value, right? In this case of the energy. Okay. But in the next class, I'll think about more properties that should remain the same and the properties that should change when this thing is happening.
Thank
Okay. Anything else, or should we just end the session for today?
you. Thank you. Thanks a lot.
Okay. Thank you so much for joining. Uh, have a nice evening. I'll see you next Saturday.
Yeah, thank
Okay.
you.
You're welcome. Bye bye.
Bye bye.